Hello, I'm Dr. Basil Considine. I'm here from the ACU Online Writing Center, and today we're going to do a webinar that was created by student request. Specifically, we're going to be talking about how to interpret some common statistics that you might encounter as a graduate student. Now, this is not a statistics course. What we aim to do here is to explain some things that you might encounter so that when you revisit them, you will have a foundation for understanding, and eventually, if you are doing research that involves these, that you will recognize when and why you might want to do certain operations. So there's going to be a mixture of vocabulary, a mixture of talking about usage, and also some looking at published work to see how people have used some of these and what that means. So let's start out by defining what we're talking about. So statistics, we are talking about information that in some way, shape, or form can be counted, can be coded, can be enumerated. And these, broadly speaking, derive two categories. There are descriptive statistics, which allow us to describe the population or sample that you're using in a study, and inferential, where we're trying to look at that information that was collected and answer the research questions. Now, it is very rare to have a whole population involved as your sample. Generally, it only works with a small group, and even if you have, say, 100 people and you are paying them to do research, that does not guarantee that all 100 people who have agreed and who have accepted money will actually do everything, or that they will do it seriously. So, for example, when you're reviewing survey data and you notice, hey, this person is answering everything with the very first answer, that will likely mean that you end up discarding that data. And so you might go from having recruited 100% of a population to not having data from all of them. Now, let's say you have 99 people out of that 100. Well, it's close to a whole sample of the population. So you would probably look at that and say, well, we think based on what we got from the 99 people that we can say pretty well what this population has because we're just missing one. Now, if we have a smaller population, say we're talking researchers at an Antarctic research station, that's a smaller group, and so not having one may represent a larger and more significant portion. And so you may have a more limited application. You may not be able to make as strong generalizations or predictions as you have a greater gap between your sample and the population it's representing. And also you might be looking at a particular subpopulation. Antarctic researchers are a smaller part of their respective scientific communities that may be less generalizable because it takes a certain sort of person who is willing to go and research in those conditions and, say, not have trees and have to live indoors whenever they're not outside in the cold. And I'm not saying that you can't find things that are applicable, but it does mean that the range of things you are inferring will probably be limited based on whether your sample is representative of the subpopulation and whether the subpopulation is representative of the population as a whole. And you don't have to look further than, say, medical research in the 1950s. A lot of that was done with whoever was around, the doctors who were doing the work, and often that was medical students who tended to be from certain demographics and generally, I would say, more fit than perhaps the general population. And so you might look at it and say, okay, here's the average person based on our sample. And now the question is, well, does the rest of the world look like that? And for much of the United States in the 1950s, you would find that, actually there are some notable gaps there. So when we're looking at describing a population with statistics, we also want to be concerned with, well, is this population representative of the convenience pool around us, or is it representative of the larger group that we're trying to apply this to? And so when we look at the differences noted under inferential here, okay, first, draws inference from the sample data to answer the research questions. So if your sample is appropriate for answering the research questions, and you have a sufficiently large sample, hopefully the answer will be yes. used to make generalizations and predictions from data. Again, it's a question of, do you have enough people and enough diversity or representativeness, which are not always the same thing. For example, if you are doing genetic studies in places that have a more bounded population, you can think of certain religious groups, or, for example, I'm part Irish. Many areas of Ireland, it's a smaller genetic pool, so if we're trying to make predictions about genetics, a more narrow, more less diverse thing may be more representative of that actual population that we're trying to make the application to. And this last one is a very important thing to keep in mind, that the exact type of statistics you're going to use will vary depending on the specific research design, what you're trying to demonstrate, and what sample you're working with. Now, you can also divide variables into broad types. These are discrete variables where you have a finite set of values. There's only a limited number of answers that you can have. So, for example, if you were doing a study, you might have yes-no questions. Okay, there's only 2 there. Or you might make it yes-no, maybe. Okay, 3. And maybe yes-no, maybe I don't know. But it's not going to have a write-in thing. That's not going to have other things. You establish how many values are available as an answer, and those should be representative of whatever you're trying to track. So in the second one, you might have Republican, Democrat, Libertarian, or other. Or you might have Republican, Democrat, Libertarian, Green Party, other. And then you look at it and say, well, we only got 1 person, so we're just going to collapse all that into 3. That happens sometimes. Or you might have just 2 options, satisfied or not satisfied. Now, discrete, you have a limited pool of possible responses there. Continuous is going to have something that is tabulatable as increasing, generally something that is in numeric terms. So height, okay. So height, if we're measuring in, say, inches with fractions of inches, that can just keep going up. However tall the thing is, that's going to be the value. Same thing with weight, length, time, and there's a kind of practical delineation where sometimes things will be coded in terms of set units and you don't do a fraction, and that will make it not wholly continuous, but practically continuous. See if you're rounding to the nearest inch on height. Now, we can also talk about how we're going to measure something, and that comes up in a few ways, but let's talk about scales because this is a point of confusion. So a scale is going to be some way that we are measuring a variable. Now, it can also refer to how we're arranging those values. And so if we're looking at a characteristic of some sort that we're trying to measure, well, that's going to be a different thing depending on, is it something that has a clear order? Is there a hierarchy? Is there a progression? Are we looking at something that is all comparative? So, for example, we could be measuring the ratio between things. How many men do we have to women? How many red cars versus black cars? Which is different than if you're counting the number of cars here, so that's just going to be numbers that are going 0 on up. And whether there are negative values that are possible. So the scales are basically how we're figuring out how we're going to be measuring something, and it'll depend on the kind of data and what you're trying to do with it. Something you'll see a lot is the term normal distribution, and that refers to something that is often called the bell curve, where it's somewhat even distribution. It doesn't need to be a perfect bell curve, but something that follows this general progression where most things are clustered in the center, and we have some outliers here. More on this later. And the idea here is that most types of data will have some sort of cluster, whether it's we're tracking grades or height distribution. You tend to have a lot of people who are closer to the average height, and fewer who are super short and fewer who are super tall. Now, there are some things that don't tend to do that. If we looked at the distribution of weight in the United States, it tends to be skewed at certain age ranges. We'll talk about skewing later. But if you are looking at sets of data that are expected to have a normal distribution, one way to look and see, does this look like it's representative to see, okay, does this data set actually resemble this bell curve? Now, you can also look at how things are departing from this, or departing from that central point, like looking at the range, the variance, or the standard deviation. And the standard deviation is a way, if we look at the left side, if we're starting with that middle where about 68% fall into this central area, well, how are the rest measured from that point? So back to skewing. So skewness is basically how things are concentrated around a single point. And in this slide here, you can see that central point indicated by the line, things are evenly distributed. So this is not skewed. The left is parallel to the right. But you can also have something like the distribution on a graphic on the right-hand side, where this is called a left-skewed distribution. So this is something that students often get confused, so I'm going to read this. If the concentration lies towards the low end of the scale, with the tail of the curve trailing off to the right, the curve is called a right skew. If the tail, that's the lower part, the tail of the curve trails off to the left, it is a left skew. So often people look at, oh, where it's high, that must be where it's skewing. It's actually where it's low on the side, that's the side it's skewing towards. Now we can look at the range as showing us the measure of a spread. So the range is going to be the distance between the smallest and the largest values in the set. So for example, if we have the set of numbers here, so we might have these numbers here, and we see, okay, the highest is 100. 58 is the difference between the highest and the lowest, which is 42. So range is just the largest value minus the smallest. This other set here, we have the highest number being 91 and the lowest is 60, so the range is 31. So range gives you an idea of the degree of difference, which may have something to do with how you are applying things, whether you choose to discard some data that's clear outliers. I mentioned that earlier example of someone who just checked the same response on all the questions. That would be an example of something where if it was just one or a small number of people doing that, you're like, okay, we were going to drop that because they didn't fill this out clearly or accurately, it seems. Now, variance. Variance is a way that we talk about how scores are different. And here's what you need to know now. The more variance, or the higher your variance value, then the greater spread you're going to have between your scores. And how do you use it? Well, that's mainly when you are going to be calculating certain statistics that, if you're doing a quantitative dissertation, are probably going to come up. Things like a T or Z test, the analysis of variance, or ANOVA, regression. Now, if you have a variance of 0, that indicates that all values within a set of numbers are identical. That doesn't tend to happen very often, unless it's something like, do you like money? Well, people tend to all say yes to that one. But in a very large sample, you'd expect that at least someone will be like, well, not always, or not sure. So you're usually going to have a variance that is different from 0. Now, if you have any variance, whether it's going up or down from this point, it's going to be construed as a positive number because that's a difference from that 0 point. Now, a large variance means you're departing from the mean more, and a small variance means there's not as much of a spread. Speaking of spread, standard deviation is one of those ways that we talk about it. And it's another way to describe it, but in terms of those standard distributions, so standard deviation works when we are looking at some sort of distribution here. We can categorize and say, okay, here's most people are within this range of values. And actually, let's go back to that. So if we see here, we have the central point would be a 0 standard deviation, and then we have 1 standard deviation in each direction, and that brings us to 95% of the values, the area under the curve, if you will. And if we take those outlying ends as well, it's going to be 99%. Now, if we are talking about these statistics, the thing that really makes it easier to remember them is asking the question, well, how do you use that? And the type of data that you're working with is going to determine what kind of measures are appropriate. And as we move to what we call higher order data, then you can do what we call higher order statistics. So let's talk about T and Z here. So in statistics, the standard score is going to be the number of standard deviations above or below the mean point. Now for z-scores, a positive standard score, it means it's above the mean, and a negative means it's below. So remember, the skewing is opposite what you think. The z-score, if it's moving above the thing, then it's going to be positive. If it's moving below, it's going to be negative. Now, don't worry so much about the description here. They're formulas, they're calculators. Right now we're talking about understanding in general what this is representing and why. And you might see z-values, z-scores, normal scores, or standardized variables used to refer to much the same thing. And again, we're going back to that question of tracking what's underneath this curve and our different standard deviations from the middle. So we're going to a higher level of precision than the previous graphic. So technically we're talking 68.2% being one standard deviation from the mean, and then a total of 95.2% being two standard deviations from the mean. And then to get the rest is we're talking in excess of two standard deviations, going to three standard deviations. And that's three standard deviations in each direction. So you can see that the outliers, you don't worry about them so much because so much is clustered. All about 2/3 is within one standard deviation if it's a normal distribution, and 95% is within two standard deviations. So let's now talk about interpretation. So the interpretation is when we look at the analysis that's run. So say you have SPSS, the stat program, and you give it some data and you run some analyses. Well, how do you figure out what these numbers mean? What do you do with them? And here we can look at some types of tests that you might be doing, like a test for difference. So is there a significant difference or a statistically significant difference between groups? And is there a relationship between two variables? And so these are ones that get used a lot because when you're testing for relationships, you're usually trying to find, does this predict that? Might this be a cause of something? Or might it tell us what to look for? And so you'll usually be doing this with either univariate statistical analysis, so you've got one variable you're dealing with, or bivariate, where you've got two. Multivariate, we're tracking more. It's not impossible, but generally people start doing that for the more advanced projects because it gets more complex. So let's talk about that. So you have some research. You have a question that you're trying to answer. One or more questions. And so in order to answer it, we need to find out, okay, how exactly are we going to understand this? What is it exactly we're looking for a result? What would that mean? But what if we don't get that result? And so we develop hypotheses to cover these scenarios. So looking at our objective, what are we trying to do? Let's say this is an education context. We're trying to find out if having a certain grade in one class predicts your performance in another class. And so your hypothesis will probably be, yes, it does. And then there's the null hypothesis, no, it doesn't. And depending on the results you get, some range of numbers will say, yes, it does. or yes, it appears to. And some range will be no, it doesn't, or no, it does not appear to do that. And exactly what that range is going to depend on our sample and the types of variables and how they're being measured. And by going through this process, if you are working with quantitative data, you know before you get the data and do the analysis what ranges of responses, or what range of on the analyses, what that will tell you. So once you've figured this out and collected the data, you do the analysis like, oh, okay, well, based on that, it's going to be a clear yes or no to your hypotheses. Now, briefly, besides your main hypothesis, the null hypothesis, okay, that isn't the case. There is no significant difference or relationship between whatever it is we're tracking. Now, you might have an alternative hypothesis. You're like, well, it might not be this. It might be this other thing. So you could be testing, all right, X is the strongest predictor of Y. But it could be, oh, well, Z is the strongest predictor of Y instead. Or your alternative hypothesis could be, oh, it's a negative predictor of this. You know, you get a high on this, you get less on that. And so you want to be stating both your hypotheses in the positive and null sense. And because it's hard to prove something definitively, usually you're going to be trying to determine whether you can reject or accept the null hypothesis or hypotheses. So while you can't say things with perfect certainty that, yes, this is causative or predictive, you can often say, well, the data seems to show it's not that. All right, a few more things before we look at some specific examples. Significance level. So that's trying to look at how likely it is that we can infer something based on the results. And the p-value is the probability. So we're looking at the significance level and saying, all right, what is the probability that this is true or not true? And so you might be using something like regression analysis or hypothesis testing. And briefly, if you've got a t-distribution, so normally distributed, that's that bell curve we were talking and looking about earlier. So if you have a data set that follows a t-distribution, and we're not sure what the population variance is, and we have fewer than 30 people, well, we're going to make some generalizations here. Now, if we have more than 30 people, we do something different, because now we can start looking at the distribution in a different way. And so don't worry about the formula here. What I'd like you to take away is that smaller samples, we use t-tests, and then if you have a larger than 30 sample, 30 or larger, you want to use a z-test instead. But it's still trying to show us that basic of, okay, can we prove or disprove our null hypothesis? And again, the z-score is simply a way of looking at how far away from that mean we are, and we just use a different formula if we have more people involved. Now, before we go further, if you have questions about statistics, I do want to plug the tutor.com service. So all students who are enrolled in ACU online programs have access to tutor.com for 10 hours free. And so they do have statistics tutors. So if you go in with specific questions, you've looked in advance and say, can you explain this to me? Or I'm trying to do this, what do I need to do? Or what does this mean? Those are things you can ask them. But let's go ahead and take a look at an article now. So I have here an article. The field it comes from happens to be psychology, and it's about employee performance. And so in this study, it's an experimental study, so they were doing some tweaking of what was going on. So if we skip down to the results, the data analysis here, we see they had a sample of more than 30 participants, 97, so they should be doing a z-score. And we see that they tell us here, all right, they did a z-test analysis, and the results were that every hypothesis they had was accepted. So if we look at their z-scores here, these are all positive. And if you recall correctly, a positive z-score means that it is supporting that. All right, now we also have some information here that we want to look at here in terms of what they're doing with it. So their conclusion here, so we see the survey was conducted on employees in the organization, and then the results demonstrated that building organizational policies based on positive psychology concepts increases the employee's performance, hence their overall productivity. Now, if we looked at this and we found that the scores were not positive, well, then that's going to be taking us in the other direction, meaning it did not support that. Okay, so now I'm going to go ahead and grab another article. Now, here we have a quasi-experimental study, and this is about applying the health belief model. So if you're in our Doctor of Nursing program, you might be looking at something like this. Now, this is a quasi-experimental study. They have 70 people, and they were divided into two groups, and they divided them into an intervention group where they did something and a control group. And so for a quasi-experimental study like this, you're trying to find out, okay, were there meaningful differences? Were there statistically significant differences? Now, it happens that they did t-tests here, and depending on who your advisor is because this is relatively close to 30, the cutoff where we might start using the z-test, you might have your professor saying, okay, you know what, it's fine, you can use the t-test. But many will also say, well, okay, if you want to publish this, this journal will expect that you do a z-test for this instead and steer you in that direction. Personally, I would have recommended a z-test for this, but you'll see a lot of literature that does this, often because it's common to have people drop out, and in this case they were able to carry all 70 people through. So they may have expected that they would end up with fewer than 30, so they planned on t-tests and then just didn't adjust that. Alright, so if we look at this, so we see they tell us they did 2 tests here. And if we look at this table here, one moment. There we are. Here's our table. We see that, while they don't have the full breakdown here, they are telling us the mean values for people's responses and the change from the mean, and what the standard deviation was for that change for each result. So 65% of the respondents said something that was within about 15 points from this 70 mean. So that's not a huge spread. And then the p-values here are telling us, okay, well, based on that, how strongly does this appear to be predictive? So we have a larger p-value here. So this one here, so you can see that they had one score after the intervention, and the spread actually increased here, whereas here the spread decreased. Now here you can see that the results, 83.42 was the mean before. The mean actually went down, and the spread increased. So yeah, that's, we're not really sure if that intervention did anything, and that's why we have this larger p-value. Now on this other one, you can see that the mean went up a lot, from 70.8 to 92.2, and that the spread was less than it was before, so we have a smaller p-value. Alright, let's look at another example. So this is a study about special needs children in Nigeria. And if we look at the abstract here, they tell us they tested 4 hypotheses, and that the criteria for whether accepting it was a significant level within this specified range. And so they used a t-test analysis to test the hypotheses, and they tell us the results here. Alright, so let's go look and see if we have a table of results or something else like that where they're specifically discussing their findings. All right, so if we look here, we have demographic statistics, and we see they have a fairly large group here. And if you're looking at this as a student in a program where you use APA style, I'll just say that this journal is not using APA style, so some things may be formatted different than you're expecting. But we look at this and we see, okay, the population was about roughly 2/3 female, 1/3 male, and skewed towards most of these being married versus single, and they divided professionalism, whether these are professional teachers or not. And then I'm guessing that there was some careful recruitment here because the teaching experience is neatly divided into groups of 300. All right, so they've listed out the hypotheses that they were testing. And you can see they have some things like they want to see whether married and single teachers had different attitudes. And okay, that's great. So their hypotheses were that there were not significant differences. Let's see what they found out. And so they have their first hypothesis, and then the results of the spread of responses, and the difference, the degrees of freedom, that's what DF stands for, and then their t-values. Okay. Now, this is something that it is helpful to have if you're writing up the results in, say, your dissertation. And not every journal article will do this because perhaps they're working with very concise word limits, but it is very helpful to tell your reader, okay, so here's the result, and here's how it compares to what we were looking for. All right, and then they follow up. They say, okay, since the calculated t-value was greater than the critical t-value, means that the mean difference between these is significant. So therefore, they're seeing, yes, there is a difference in attitude based on gender. And so they say here, okay, because we found that difference, hypothesis 1 is being rejected because they found that significant difference. So basically, they found that they proved their null hypothesis. All right, now if we look at the other results here, let's go down to hypothesis 4. So we're looking at the difference in teaching expertise, and we find that they say, okay, here are the base numbers, here's the analysis, but it was less than the critical t, meaning it was not statistically significant. So even though they found a difference, they could not say based on the results that it looked like that wasn't just due to chance. So since they essentially had a null hypothesis as their main hypothesis, they accepted that. So while usually you'll be asked to write things in the positive with the null being the no it's not, in this case they had it flipped, and so essentially they're upholding what would be the null hypothesis in the standard arrangement. To put that another way, what they've presented as their hypotheses, most stats classes will tell you to present as your null hypotheses, but at the end of the day, so long as the wording is clear, you can do it in either direction. All right, let's look at one more example. So this is an example that's coming from a medical science journal about cancer. And we see that they used Excel for recording the data. Then they plugged that into the SPSS statistical software, which, by the way, you can get free access to at ACU. And then they ran z-test. And if we look at the sample size of 100 nurses, then the z-test is very appropriate for that and would be the recommended better practice here. All right, so now if we look down here, they tell us some demographic things here. But what we're interested right now is looking at this information here. So they pulled people and they looked and said, okay, frequency, that would be N, That's just the number of responses is who said they had knowledge of that. This is the percentage of the respondents who said that. Now here's our z-value, and then their probability here. Now you can see that we have greater than and less than. And we're going to look at the pane as a practical illustration of what that matters. But basically, if the number is above the threshold, it suggests something. If it's below, it suggests the opposite. So let's take a look at the results for. So here we have the number of respondents who mentioned that, or this. And then if we go to our conclusions, there's less of a write-up here because it's more reporting that. But it says, okay, our data suggests that levels of knowledge and understanding should be improved. So even if you don't remember offhand which p-value direction, is it supposed to be below or above? And the answer is below. We can see, looking at this here, that the frequency of the greater than versus the less than, well, we have far more less than, but it's still, we have some things where they see, okay, yeah, there's room for improvement here. And so in this case, we see it's this very low value, only 12 people out of their sample of 100. So looking at that, we can see, okay, well, that's a very small thing. So you can say with great certainty, yeah, that is an area we could really use some improvement in. Now, if we start looking up here, well, that's a majority of people, then it makes sense that that might be a larger. All right. Now, that's not the only way. You can see here where they presented an example thing where they're breaking down the percentage to illustrate the point here. And so you'll often see more than one way of presenting data. And some of that's readability for the audience, and some of that is giving people the opportunity to engage on different levels. So say their focus was on cancer screening, and you can see from the title of this, awareness and knowledge of cervical cancer, this is the central point. There were related things that they were asking about, as you can see in these different factors here, but it's leading to, okay, do they know about this main screening test here? So, let me briefly mention some of the other things that we have here. So we do have sessions, webinars that have been recorded about formatting your output from SPSS, about how to interpret some of the data, and we will have additional things about how to write up your results coming up in the winter 2023 terms. So I hope that this has been helpful. This webinar was presented because of students such as yourselves who wrote us and requested that we talk about, that we explain, that we show some of these different things that you may have to do as a student. So if there's something like that that you would like, just go ahead and send us an email. You can contact us at onlinewritingcenter@acu.edu, schedule an appointment by going to my.acu.edu and selecting Online Writing Center from the drop-down, or visiting the Online Writing Center website and navigating from there. With that, have a great evening.